percent. This is it can fit in a lot of places. I'm putting it here simply because it's something that we need to be able to do and calculate, and next week when we're working on some labs, this is going to be useful to us. So percent yield is a ratio of experimental to theoretical amounts. Okay. Now experimental, this is what we get in our experiment. Theoretical, that's what's calculated, and you can write this down. Theoretical is the amount, I mean it says here the amount of product expected, but it's going to be calculated using stoichiometry. Okay, and so when we are doing any kind of question where you're asked for percent yield, it'll be worded something along the lines of you actually got this amount, but you should have gotten this amount, kind of an idea. So you actually got 19 grams and theoretically you could have got 20 grams. Or you might actually have to do the stoichiometry, where it says predict the amount you should get. You actually got whatever amount. What is your percent yield? Okay, it's actual divided by the theoretical times 100%. Okay, so here's one example. 6.78 grams of copper is produced when 3.92 grams of alumina reacted with excess copper-2 sulfate. This kind of is a great review of lots of things. Okay, so copper is produced, that's one of the products. Okay, aluminum. So the very first thing we need to do is we need to write out the balanced chemical equation. Okay, and so we're reacting aluminum with copper-2 sulfate. And it's going to make, it's a single replacement reaction, it's going to make solid copper, and it's going to make, plus aluminum sulfate. Doesn't specifically state it, but I can tell you that this reaction is going to work best in an aqueous environment. We've actually tried to do this one near the beginning of the year. If the aluminum is old or it has coating on it, it doesn't always work all that well. Anyways, that is my unbalanced chemical reaction. We need to balance this thing yet. And so, let's see here. We can start with getting the aluminums balanced. Let's get the sulfates balanced. Get the coppers balanced, and we're done. Now, what is the actual yield? Well, the actual yield is 6.78 grams of copper. Theoretical yield, we have to do, now, excuse me, easy mistake to make is to think, oh, theoretical yield, that's that. No. Theoretical yield, we have to do stoichiometry to get to. And to get to the stoichiometry, we have to figure this out. So we actually have to do the calculation. So the mass of aluminum is 3.92 grams. Okay. We're reacting it with excess copper-2 sulfate. This is important later on. We'll talk about this idea of excess. It means basically that there's more than enough copper-2 sulfate to react with all the aluminum. Okay? Because we don't want to run out of copper-2 sulfate and have, enough copper-2 sulfate to only react with 3 grams of aluminum, because then we don't get as much product as we should. Okay? So theoretical yield here. So here we have to figure out, well, we want to find out the mass of copper. Okay. And you're going to do your stoichiometry. And there's not a lot of room up there, but you guys should be able to do this. Even if you don't have the notes in front of you, you will have them emailed to you, but there's only 2 pages worth. So do the work. Pause it right now. Do the work. Okay, I'm serious. Pause it right now and do the work. Okay, so aluminum, there's our molar mass. Copper, there it is. We'll need those for what we're doing here, but not on this file. Let's go to this one. So, mass of copper. And again, I'm doing it the second way, the shortcut way, doing everything all at once here. That being said, it's very easy for you. You'll get the same answer whether you do it my way, this way, or using the formulas. Okay, so I've got 3.92 grams of aluminum times 1 mole of aluminum. No, let's try that again. Yes, sorry, I'm thinking ahead. 1 mole of aluminum per 26.98 grams of aluminum. Okay, multiplied now by my mole ratio of what I want. Well, I want to change this into copper. So 3 moles of copper per every 2 moles aluminum times 63.55 grams of copper. Again, this is my molar mass of copper. Grams of copper per 1 mole. That might look like an A, but it was supposed to be a U. Copper per 1 mole. Alright, so we'll plug the numbers into our calculator here. 3.92 times 1 times 3 times 63.55 divided by 26.98 divided by 2. Okay. Theoretical yield is going to be 13.9 grams. Okay, that's my theoretical yield. Sorry, and I've jumped ahead. I ran out of space. What is my percent yield? Well, I go back to my formula. Actual divided by theoretical times 100%. So my percent yield is going to be 6.78 grams. That's my actual yield. Divided by 13.9 grams. That's my theoretical yield. Times 100%. And that is going to be equal to something in the neighborhood of 50%, but let's find out the actual answer. Oops. 6.78 divided by 13.9. 48.8% yield. Which might seem a bit low, and I would agree with you, it does. There's many reasons why it could happen. We'll look at them. So percent yield tells us how efficient a reaction is. Now percent yield cannot be bigger than 100%. Now why is the actual yield less? Couple things we could talk about here. One of them is that measurement uncertainties. They're often small, but they still exist. Another reason is the purity of chemicals used. What we buy for school experiments are not the purest chemicals that you can get. Usually they're anywhere from 95 to 99% pure. If you're doing laboratory analysis, like you might see on some forensic show on TV, there you're paying a lot more for your chemicals that you use. You're getting things that are like 99.9%. Or if you want to pay the real premium, you go 99.99% pure. Okay. Another reason might be if you wash the precipitate. This is something that's often done, is you'd rinse off the precipitate to make sure that you only have precipitate. If you wash too vigorously, you might lose some particles. Another reason would be estimations you've made along the way. So you might estimate that the reaction actually goes to 100% completion. Maybe it didn't. Maybe this reaction that we just did, you had 3.92 grams of aluminum as a big chunk. The outside part of it has all turned to copper, but the inside bit in the middle is still solid aluminum that's coated with copper. If that's the case, it's quite probable, in fact, that it will not be anywhere near 100% efficient. Okay? So that's percent yield. It's related to stoichiometry. We're going to use it at several points along the way. All right, this takes us to kind of the last kind of stoichiometry. We're going to apply some things with this yet next week, but this is the last big topic. Okay? From a practical standpoint, we usually solve stoich problems that are quantity of something to quantity of something. Whether it be quantities of moles, mass, volume, or concentration. Now, we've already taken care of moles and mass. We can go from mass to mass, or moles to mass, or mass to moles, without too much problems. What we're going to add to the mix today is, what about volume of gases? Or concentration? Okay. And we can even have complex combinations of these problems where you have certain mass of something is being turned into gas. What volume of gas will be produced? Those types of things. I say complex, they're not really all that hard. It just means you have to think as you go. That being said, no matter what we're doing, you're going to go from the quantity of whatever you start with, whatever you're given, you change it to moles. Every time you do this, you're going to change whatever you're given into moles, if it's not moles already. Then you use the mole ratio to turn the moles into the moles of whatever you need, and then you use some kind of conversion factor to turn it back into what you want. Whether it be the molar mass, to find out the mass of something. Whether it be the ideal gas law, to get back to volume. Whether it be concentration, and the C equals N over V formula to get back to concentration. Okay. So you've done a question like this, but that's okay. This is mass to mass stoichiometry. But it would be a good one to practice. So how much copper is required to produce 25.8 grams of gold by reacting solid copper with gold 1 nitrate? So how much copper? So we want to react solid copper with gold 1 nitrate. So copper solid plus gold 1 nitrate. AuNO3, which will be aqueous. How would you tell if it's aqueous or not? Well, we're going to assume, again, reactions like this, where we have a solid reacting with some kind of an ionic compound. You can always assume, unless you're told otherwise, that they're taking place in an aqueous environment. How do we know this particular substance is aqueous? We'd use our solubility table. Okay, this is going to make us copper. Now in this case, we have to actually make look at our periodic table. We look here and you see copper. And you'll notice that there's 2 plus and 1 plus. Now, it doesn't tell us. We have to predict which one it's going to be. But if it doesn't tell us which one it's going to be, it's going to make copper nitrate of some kind. The more common one is the 2 plus version. That's what's going to be made. Okay? So it's going to be copper 2 nitrate. So CuNO3 2 times. It's a nitrate. It's going to be aqueous. Plus gold, which will be a solid in this case. Right. Next step, we got to balance this thing. Okay, so we balance it. We look, nitrate. Okay, we need to have a 2 there, which means we need a 2 there, and that should do the job. Okay. Now, how much copper is required to produce 25.8 grams of gold? So we're told we need to get 25.8 grams of gold. We want to find out the mass of copper. Alright, so we need the molar mass of both of these things. Oops, wrong one. Okay, molar mass of gold is 196.97. There's copper, 63.55. Okay, so for gold, 196.97. Okay, if you've been just copying down up till now, pause this, do it for yourself. Chemistry is not a spectator sport. It's very easy to think you know how to do chemistry when you watch somebody else do it, but until you try to do it for yourself, you won't know if you can do it or not. Alright, so let's figure out our moles. Again, we can use either method. This time I'll use formulas. I won't quite fill in all of the spots. Okay, so I would actually, if I was showing all my work, have to show that I'm writing these numbers in. However, 96.7. So we have 0.13. Leave the big number in your calculator. Dot, dot, dot. Moles, 1309 something. Okay, we need to know how many moles of copper. So the moles of copper, that's going to use the molar, the molar ratio, or the mole ratio. It's going to be equal to, so our 0.13 moles of gold. Again, we're keeping the big number in our calculator. And then we look at our coefficients times. What do we want? We want copper, 1 mole of copper per 2 moles of gold. Right, so our moles of copper is going to be equal to 0.0654. And so our mass is going to be moles times molar mass. Again, keep the big number in your calculator. And we should need 4.16 grams. Now, why is it such a big difference? Well, it's because gold is much heavier per mole than copper. And also, 1 mole of copper makes 2 moles of gold using this reaction. Perfect. So that's what we've been doing, gravimetric stoichiometry. Now, in reality, if all we put in was 4.16 grams of copper, we probably will not get 25.8 grams of gold. We need at least 4.16 grams. Remember what we were just talking about with percent yield. Rule of thumb is to add about 10% extra. So 4.16 plus 10% of that would be a good rule of thumb. Where that breaks down is if you've got something that's a really expensive reagent, then maybe you only add 1 or 2% extra. Okay, now when working with gases, you can utilize STP and SATP molar volumes. At STP, and this is on your data table, 22.4 liters per mole. At SATP, 24.8 liters per mole. Okay, and again, I mean, this is another chart similar to what we've been dealing with. This part here, okay, moles of reactant to moles of product. That's the central part of this all. Okay. Now, continuing. Hydrogen gas is produced when hydrogen metal reacts with water. What mass is required of sodium to produce 15.6 liters of hydrogen at SATP? So hydrogen gas is produced, that's the product, when sodium metal reacts with water. Okay, so we've got sodium metal, Na, solid. I know some of you are complaining about the A, you'll be okay. Plus H2O. Liquid is going to give us hydrogen gas and sodium hydroxide. And we need to balance it, so we're going to need two goes here. Which will produce our 2 moles there. We need a 2 here and a 2 here, and then everything's balanced. Okay, so we need 15.6 liters of hydrogen. Now, a couple ways we could do this. You can find out the conditions of hydrogen at SATP. So find out the pressure and temperature. Okay, that's perfectly valid. Use the ideal gas law. The easier way is to say, okay, knowing that it's at SATP, 1 mole has a volume at SATP of 24.8 liters. So we need mass of sodium. We're going to need the molar mass of sodium, which is 22.99 off our periodic table. And we need to we want to look for the mass. So our mass of sodium, I'm going to do this both ways here. Mass of sodium is going to be equal to, well, what do we start with? We've got 15.6 liters of hydrogen. And we want to change that to moles. Times 1 mole of hydrogen, because it's at SATP, per every 24.8 liters. Okay, so now we've got moles of hydrogen, right? Liters of hydrogen are gone. And now we need to look at we want to find out moles of sodium. So we've gone from what we're given of hydrogen into moles of hydrogen, right? Our liters of hydrogen, sorry, I can write that down. Our liters of hydrogen cancel. Okay, now we've got moles of hydrogen. We want to change it to moles of sodium. So 2 moles of sodium. For every 1 mole of hydrogen. Now our moles of hydrogen are gone. Lovely. And now we need to figure out how mass of hydrogen. So times 22.99 grams of hydrogen for every, grams of sodium, my goodness. Grams of sodium per mole, per 1 mole of sodium. And moles of sodium go away. And there we go. And so our answer here, 15.6 times 1 times 2 times 22.99. And then we have to divide that by 24.8 and divide that answer by 1 and by 1. And so we should be getting 28.9 grams of sodium. And then we can kind of go back and look and say, okay, 15.6 liters. Okay, well, 1 mole would be 24.8, so this is over half a mole. And we look and say 1 mole of hydrogen will produce 2 moles of sodium, just looking at our coefficients here. Okay, so we've got about a half mole or a little bit more. So 22.99 grams, if it was exactly half a mole, would be produced. Yeah, so this number works. Okay, and that's just a way of making sure that we're actually on the right track. Alright, so here's another example. Sorry. And you can do all of the calculations. I will show you the one calculation to go from molar volume, or from volume here into number of moles. And if you think back to the gas unit, you can look up and find that, find this equation. But your molar volume, or what we called Vm, is equal to volume divided by moles. Okay. Now we want to find out N. And so N is going to be equal to the volume we're given, V, divided by Vm, which is going to be equal to the volume we're given, which is 15.6 liters of hydrogen, divided by the molar volume, which is 24.8 liters per mole. And then our number of moles of hydrogen is going to be 15.6 divided by 24.8, which is 0.629, and so on. Dot, dot, dot. Moles of hydrogen. Then you will use your mole ratio, just like you've been doing all along, to figure out how many moles of sodium. Then you use your N is equal to little m over big M, and rearrange it to solve for mass, and away you go. Okay. Let's take a look at this one here. Ammonia can be produced by reacting nitrogen and hydrogen gas. What volume of ammonia at 426 kilopascals and 90 degrees Celsius can be obtained by reacting 7.5 kilograms of hydrogen with excess nitrogen? So ammonia reaction between nitrogen and hydrogen. Okay, so we have N2, that's my nitrogen gas, plus H2, that's my hydrogen gas. And that's going to produce ammonia, also a gas. Now here we're given the specific pressure and temperature, and so we can't use this because this is not SATP or STP, but we got to balance it first anyways. We need 2 of those, which means we'll need 3 of those. Now we're told our mass of hydrogen is 7.5 kilograms, or 7,500 grams. Why did I change it to grams? Well, our molar mass is in grams per mole, so molar mass of hydrogen gas It's H2, 2 times 1.01. I can do that in my head. It is 2.02 grams per mole. This one's a little bit harder to do my long, make one big formula with it, so I'll show this with the smaller individual formulas. And we want to figure out volume of ammonia at this particular pressure and temperature. Be careful, we're going to be using the ideal gas law. This needs to get turned into kelvins. So we have 90 plus 273.15, so that temperature is 363.15 Kelvin. Alright, so let's go with this. Number of moles of hydrogen. Okay, we've got mass, we have molar mass is equal to little m over big M. We fill in our blanks. 7,500 divided by 2.02. This is going to be big number, by the way. Divide by 2.02. Lovely. 3,712.87 and so on. Keep the big number in your calculator. Okay. And moles of ammonia will be equal to 3,712 moles of hydrogen, point whatever, 0.8 moles of hydrogen times 2 moles of ammonia per 3 moles of hydrogen. 2 moles of H3 per 3 moles of H2. So my moles of ammonia are going to be equal to 2,475. It's kind of a fun number because it's 0.2475 anyways. Moles. And then we use our ideal gas law, PV equals nRT. And we're going to solve that for the number of, or sorry, the volume of ammonia. Alright, so here's my numbers plugged in case you're curious as to where we got them from. 2475.2 moles, that's the moles we figured out using our mole ratio. R is our 8.314 kilopascal liters per mole Kelvin, the ideal gas constant. And temperature, we figured that out earlier here, 90 degrees Celsius, but you gotta convert it to kelvins. 426 kilopascals, that's given to us. So those are our numbers there. Okay, so we multiply them through. And we end up with 17,543.05 liters. Now we look, okay, 2 significant digits. So we're going to have 1.8 times 10 to the 4 liters. Or, if you'd rather, 18 kiloliters of ammonia in this reaction. Okay, solutions work in much the same way. Okay, alright, so I got this set up here. The idea here is at this point, see what you can do with this. You know that you're given enough information here, you should be able to convert this to moles. As soon as you can convert this to moles, you can figure out moles of this ammonia. Once you know moles, you have concentration, right? Remember, C is equal to N over V. If you have C and N, you can find V. Okay? Alright, so at this point, what I've done is I've solved for the number of moles of phosphoric acid, H3PO4, by multiplying concentration and volume. That gives me moles of this thing. I now need to find moles of the other thing. And so my next step now is simply to figure out the volume. And volume is going to be equal to N over C. So my moles will be my solution to this little problem, 12,900 times 2. And my concentration is given up there. And so when I'm done all of this, 12,900 times 2 is 25,800 divided by 14.8 is going to be equal to 1,743.2 liters. Now looking back here, I need this to 3 significant digits. And so this should actually be 1.74 times 10 to the third liters. Okay. And our very last one. Pause the video at this point. See if you can figure this one out on your own. Remember, this is moles per liter. This is milliliters. So you're going to have to convert from milliliters into liters. These are both in milliliters. This is in moles per liter. Alright, so at this point here is our balanced reaction. Okay, our next step, we have C of this is 0.150 moles per liter. And volume of this is going to be 0.0159 liters. Volume of acid is given to us 0.100 liters. We need concentration. Set this up, and what I've done is I've set it up like it's the C is equal to N over V, where I'm looking at the number of moles of H2SO4, which I figure out using the concentration of potassium hydroxide to figure out the moles of potassium hydroxide, and then I multiply that by the mole ratio. Okay, that gives me this top bit, which is my number of moles of sulfuric acid. And then I'm given the volume here. That goes on the bottom. And so I punch in all my numbers. 0.0159 times 0.150 times 1 divided by 1 divided by 2. Okay, gives me a tiny number, 0.0011925. That's the number of moles. Divided that by 0.1. And my concentration of H2SO4 is going to equal 0.0119 moles per liter. Right. And at this point, you guys have a worksheet to work on. Lots of practice on this. Lots of practice with gravimetric stoichiometry. You need to get it all done by Monday. There's lots to do. I realize that. I realize it takes time. But the only way to get good at this stuff is to practice it. So use the rest of your class, practice this. You're going to have some homework. This is getting you in shape to practice and get ready for your final exam. Because we're reviewing right now concentration. We're reviewing balancing equations. We're reviewing solubility. We're reviewing ideal gas law. We're reviewing molar volume of gases. We're reviewing going from name to formula. Okay, we're reviewing predicting reactions. It's a great way to do review anyways. Thank you.